Hi everybody, my name is Matt Schuetze. I work for a company called Azul Systems. I have to vouch for Heather as being an actual adopted JSR lead. I'm trying to get the Detroit jug to go through the process. We submitted our signed JSPA last week and it's up for approval. So she's right, the wikis walks you through the steps, and when I did the show of hands, how many people want to do this? Everybody said, me! So you guys are pretty timid in comparison. But it's interesting to be that close to the cauldron where the next Java is brewing. You can actually participate and play. In addition to having 3 talk speakers here tonight, I actually have 3 speakers here virtually. I have 2 co-authors that actually wrote this presentation. I'm just the one that gets to present it tonight. This talk, low latency Java in the real world, is interesting because we'll break it down into the parts of the title. Low latency, really, for Java? Yeah, really, for Java, and it is in the real world. This is going to be a case study on a real live trading platform implemented fully in Java that is hosting production traffic. And the talk was given last week in London at QCon by Mark Price, who's a senior developer at LMAX Foreign Exchange, and Gil Tene, who's the CTO of Azul, which is where I work. So they couldn't be here. They're off doing other things, obviously. But the talk was the first time we've ever done a joint session with a customer, and so I captured their notes. It was probably a little more interesting to have us and our customer on the same stage. You got me, so hopefully that's okay. And I can represent LMAX, even though I don't work for them, in using the words they provided last week. So if you don't know Azul or Gil Tene, Gil has spoken to this group before. Any of you work in the larger banks in town, he's given private sessions in most of them. I spoke for him last year when he was busy in another city. And he's pretty much the founder of Azul and does a good job of explaining latency in a way that is either very encouraging or it's depressing when people realize what latency really means in terms of real systems of Java running on Linux, on real Intel, on real hardware, and the problems that can happen if you don't take into account certain aspects of measuring systems and underlying system behavior. The co-author, Mark Price, is interesting. He's touched almost everything in the exchange at LMAX, very focused on performance and monitoring, but he's the guy where people would come with their GC logs and say, Doc, I got a problem. So he heard nothing but pain points over and over. So he's a good person to actually speak about how Azul Zing, the JVM that you can put in situations like this, to alleviate the pain of garbage collection and other pauses that would prevent you from having a beneficial and productive life doing low latency Java. I'll say it that way. So who am I? Like I said, I actually was here a year ago. I spoke last March. So thanks for having me back. Frank hasn't kicked me out, so I'm back again. I'm the Director of Product Management, so I do a lot of taking requests and requirements into our engineering teams, and then once we build new versions, take it back out to you guys and explain what we did and why you should use it, or at least know about it. And then I also participate in the greater JCP. Although Gil is our actual named Azul representative on the executive committee, I'm his alternate. So I've been to the JCP meetings. I can vouch for Heather and for the rest of the JCP that it is a very open organization with both individual and corporate and nonprofits or non-commercial interests participating. And I also just in the last year stepped up in my home city, which is Detroit, to actually help the guys there run their jug, and I'm starting to take them into the adopted JSR process as of our January meeting. And I will admit it, I stand on the shoulders of giants. I mean, this work, the effort here is for the rest of this talk is the other authors. But I do have the benefit of saying, yes, I am a product manager, so I know what it's like. And the last 2 years with Azul has been a very vicious bike ride. I'll say that. This is actually a sweatshirt you can buy on the web, by the way. I just like the imprint. So now to get into is that a decent intro? Kind of know where we're coming from? Okay. So LMAX. All the banks have trading floors or equivalent. There are exchanges in addition to New York and NASDAQ and the other equities exchanges. But so LMAX is a foreign currency exchange based in the UK. Their goal is to be it's a multilateral trading facility. I had to learn that, what that acronym means. It means an alternative trading floor. But very popular, fast-growing company, and they want to be the fastest retail exchange. And it's very open. They actually are the authors of the Disruptor framework. One of their lead alumni is Martin Thompson, who runs the Mechanical Sympathy blog. So, and they'll tell you exactly, in fact, you're going to see in a few more slides, they'll explain their matching engine. They'll explain how they do what they do, and they're very open about it. And what's interesting is most of our other customers are very hush-hush. To actually have someone say, this is how we do it using Zing was very nice for us because it kind of peels back the shroud of secrecy that a lot of our other customers drop on us, so where we can't talk about it. So it's very exciting to have them stand up and say, we use this and here's how. So a lot of the rest of this talk is going to be going into their architecture to see how and why and where they can use Java. They can use open source jars, they can use their own code, it's nothing special, but they use Zing underneath to take away the pains of continually tweaking and tuning and suffering through weird latencies that would otherwise disrupt their customers, which are the traders and the market makers. So, apologies, I know you guys are here to learn something. This isn't supposed to be a marketing pitch, and I'm sorry, but I have to explain what Zing is. Zing is an alternative to the Java that you might get from the other major JVM vendors. Its purpose in life is to take away the little jitter and stalls and hiccups that can happen in traditional JVMs. And so the way we've implemented our garbage collection algorithm, almost all pauses due to garbage collection are taken out of the running Java threads. It's all handled concurrently. And you can therefore use this for both human scale latencies, where you don't want to have humans waiting for things that are jerky and frozen and stalling, or for machine-to-machine low latency, like in a trading exchange, where orders are zipping in really fast and they have to be acted on with sub-millisecond response. The other interesting thing about the way we approached building this JVM is we've decoupled scale from pause. So normally when you think of, well, I can't run my heap larger than 20 gigs because the GC pauses get long. Well, that's true in traditional GC, the ones that are in OpenJDK and some other JVMs. We actually have decoupled that. So big or small, high or low, the pauses are not there. Or the pauses are down to the level where the real pauses that are remaining are mostly operating system, not JVM. So we like to say that, yeah, there's all these developments that are happening for GC in the world. There's Shenandoah, there's some other projects. Just Shenandoah. But we think it solves, because what happens after you solve GC, there's a whole other raft of new things that crop up to be the next issue of latency. So the other aspect is, if you write code in Java, you can write code in Java. You don't have to dance around writing things that are in Java, the language, but you're doing your own pre-allocation, or you're basically managing your own memory in spite of the garbage collector. That's not supposed to be how Java works. You're supposed to let the garbage collector do that sort of checking for you. So one of the benefits of being able to remove a lot of this jitter and pauses is that you can stay responsive in the wake of load. So this is an LMAX example. Currency exchange between euros and Swiss francs. Swiss central bank makes an announcement midday. This is January 15th, so a couple months ago. Midday, there's a spike. The volume jumps from a floor of, I don't know, some average garden variety trading to 7 times its value for a brief couple of minutes. And then it sustains about 4 times its normal load throughout the rest of the trading session. So it's an unplanned event. You didn't know it was coming. And yet, even when the patterns changed, the exchange kept running and the latencies felt by the market makers and the other traders was negligible. It just kept working. So how many times have you ever had traffic jump on you like that and suddenly things get squirrely? This is, they stood up and said, nope, we can handle this, we can handle the load. It's not just a garbage collection problem, it's also an allocation speed. You have to be able to do both. Allocate quickly and stay ahead of objects that are out of scope.
What was that actual volume?
Oh my God, you're gonna make me look at the notes.
7 times 100 is not that much.
I don't have the number.
It was easy.
I think the notes on the next slide have, yeah, shoot. This is where I would turn to my friend from LMAX, who would be able to tell you the exact metrics, because that's his data. I think we will answer that when we talk about the actual architecture. Sure. A bit closer. This view is another, this is now we've zoomed in closely to show that traffic is not constant. Traffic has bursts. This is no longer the span of a day. This is more like a span of 4 seconds. So you can see that there's a spike on the second. You can see that there are other spikes on the quarter second. So some trading algorithm, some order flood, some behavior on the market makers is leading towards very high things as the second is rolling over, and apparently every quarter second. So it's not constant. If it were constant, it would be where the red line is. And I think this is down in the 300 microsecond is about where that average is. So the peaks are probably about 900 microseconds, so less than a millisecond. They're down that low. They're trying to be as fast as they can be. So it's not constant. It's not a constant flood. It's a bursty model of traffic, but it's not random either. It's not a stochastic model. There's a pattern. The pattern is just not regular. It's not normal. It's not Gaussian. It's somewhere in between a sinusoid and noise, but it's not either. So when LMAX actually rolled out their product or their exchange, it's been composed of several different paths of data. And again, my apologies, I wish I had Mark here. In fact, next time Mark and Gil get together, they'll go through this, and maybe if it's QCon here in New York, they'll go. But anyway, this is a block of texture diagram of the exchange, and there's 2 main paths. The market makers are the actual people that provide liquidity to the exchange, come straight in to the matching engine, and the other sets of retail customers and web customers come in first through the pre-trade risk side and then to the matching engine. So they have a little bit longer latency path. But the cuteness is here, where we actually show what happens when a packet comes in. So this is the packet of crisps that just arrived in from the market. It moves through the gateway, down to the matching engine. When it hits the matching engine, it splits for redundancy. One of them then goes to the secondary. They both go through the logic of the match, and then I guess another copy stuff to the journal, and then they're joined again to go back out, and that completes the order. And then it's the same thing on the other side, except for customers and web traffic, using either fix or HTTP, they'll go through the risk, pre-trade risks side first. So there's nothing revolutionary there. Oh, and that's the other point. Those little snail shell things, those are lockless queues, the disruptor frameworks. So since they invented the framework, they use it wherever they can. And so there's a 1 or 2 or more in every one of those tiers. So really, you can use Java for low latency? And the answer is yes. Java is great for a lot of reasons. You win on factors that have nothing to do with the latency side. You win because of time to stability. You win because of time to market. You win because you can actually get good performance. Those are really important things to actually innovate and come out with improvements, changes, benefits to your business, and the downsides historically can be overcome. The entire exchange is in Java. There's no C or C++ or magic underneath. So the whole thing is now pure Java. But with the good comes some bad and ugly, and LMAX would say there were some warts to get to where they are today. It's very good. Java's fast. I mean, Java actually has a really strong JIT compiler in it. The compiled machine code is optimized. Good developers can write good, fast code. Bad developers, doesn't matter what language, they'll produce slow code. And there's more Java developers available to work in places like here in New York and others than there usually are C++ devs. That's both good and bad. But there's a lot of Java experience you can tap even in something like this, which is theoretically low latency. It doesn't have to be special, it's just Java. And the thing about the JVMs, they are normally not consistently fast. They can be fast, but they have this inconsistency problem. And GC is the one we throw out a lot, garbage collection, it's got its pauses, but there's more. There's also the effect when compiled code gets recognized as being non-optimal and it gets recompiled. Well, it takes a step back called de-optimization first. That's another source of latency, it has nothing to do with garbage collection. And then deflation is an aspect of locks. So, oh my, whoa, there's lots of things that can interrupt consistency. And so people that are doing low latency, air quotes Java, are rolling their own and avoiding just common, everyday, plain, readable Java code. And therefore, you can't use anyone else's. You can't drag some open source. You can't take a new developer in until they get indoctrinated into your style of either allocation list Java or other magic. So it gets as challenging as doing it in C++ or worse. So what is it? How does it help to drag in Zing to this equation? It's pretty much a drop-in. You change your Java home path, and if you're on Linux, you're good to go. But the value is its consistent speed. There's no hiccups. We've spent the last 12 years as a company and probably 6 years on Zing itself to grind away anything within in the JVM. So what's left is noise that's even below OS noise. We're keeping the good parts of Java. It's the same language, it's the same classes, it's the same behavior, it's the same, you can walk the tree from bin to lib to JRE to etc. It looks very, very, very similar. And it removes the bad and the ugly. The stop the world pauses, the intermittent behaviors, and it also takes away all of the pain as a developer that you would otherwise spend getting around the GC nits. So it's regular Java that you can code in, not just air quotes Java. So let's talk about how LMAX got into this. They started about 2 years ago. They went to the most critical system first, and then went through everything in the latency sensitive path, and then started to look at other things that touch the throughput of the sensitive path. So The latency critical path is where that the package of crisps went. It goes through the latency sensitive path, but there's other things that can happen when the trade information goes like to the market prices and to the other monitoring nodes. Well, they care about throughput, not about latencies, but if there's any back pressure from outliers there, it gets felt in the latency critical path, and new outliers can come back in, which the market makers feel. So they had to go back all the way through. So looking again at the block architecture map, we've got the exchange and the gateways, but then also the data history and the surveillance. The order that LMAX attacked this was go after the matching engine first, and the secondary, then go at the risk checking system, finally the 3 gateways, and then just for good measure, they just kept going. Like they just put Zing everywhere. Because it turns out those systems, even though they're not in the latency critical path, can lead to back pressure on the latency path. Sorry, latency sensitive path. And interesting, there's a couple of, let's talk about LMAX as a Java shop. They're very focused on test-driven development. They're very focused on continuous integration. They have a whole range of functional tests, and they treat performance bugs as just another part of the CI system. So if there's a regression in performance, it gets red flagged, it's treated like a critical bug. And so the slightest degradation or introduction of new hiccups gets squashed immediately. And that gives them confidence to make large changes, like swapping out the whole GVM. What they found in cutting over to Zing were improved behaviors, actually reducing engineering effort because they weren't firefighting and tuning battles, or rolling their own GC-friendly code. And being able to just write and use regular Java was huge. They didn't have to do any special practices. They got to ease up. They already had disruptor, so they already had the lockless queue, but now they could give up on the no allocations because GC would keep up and it would stay out of the way. And they can leverage third-party code, which otherwise you wouldn't be able to do. So it's an overall more productive environment. The lesson learned is they attacked the critical things first. So going after the matching engine, think of all the man hours, man centuries that went into the engineering of that thing in the first place. It was already really darn good. So by going there first, they didn't see a whole lot of benefit in terms of overall like speed up, I'd say. So it was very marginal gains. They had already wrung out a bunch of issues and already done a bunch of good engineering. So it took a long time for them to believe, okay, Zing is working for us here. With hindsight, we could have gone outside in. Do the less critical things first and get some fast wins because they weren't as critical. They didn't have as much engineering. They probably had some slack to show benefit right away. And it would have given time to build in confidence because you made a change, it's working, it's better. Okay, let's try the next one. You take on the higher risk things. So we might have gotten through the process faster. It actually took 2 years from beginning to end to get all of those different systems outfitted. There's also some other lessons. GC is not the only problem. It's natural to think that it is, but once the GCs are gone, there's more behind it. They had issues with page caching at the kernel. They actually realized they needed to bump up a kernel version. They had power management switches in the BIOS they had to ring out, and then other items. And then also they built a whole litany of things we learned about Linux. So out of the box, Linux itself is not good for low latency. You got to make some other changes. Change the page cache size, turn off transparent huge pages, set swappiness to 0, and set zone reclaim info to 0. Each of these can introduce 100 millisecond or more latency. Yeah?
What version of Linux are we talking about?
I don't actually know the OS, but Zing is qualified on all of the commercial distros, Red Hat, CentOS, SUSE, Ubuntu, Debian. Most people are running on Red Hat, but not everybody. But it's the stock version. You can also put it on, I know we can put it on the Red Hat real-time, but so there's other variations. The thing that happens though, pauses like this in the 100 millisecond range normally were chalked up to garbage collection. So once all those are gone and these pauses still remain, what were they? So having to identify things that weren't in the JVM became the next interesting part of the puzzle. And so, measuring was a big deal. We have a whole series of talks about how to measure latency in Java. And so triaging the cause of each hiccup, especially as data's packets are moving between the different tiers, and recording all of those interactions. So the upshot is LMAX, trust Zing. We love LMAX because they're using it fully. They actually would stand behind these sort of real world results. They tame their GC outliers on their highly engineered system where they were having 4 millisecond pauses every 30 seconds. We got it down to below 1 every 2 hours. So that's a big improvement across the exchange. On the less well-tuned systems where they would have bigger latencies about as frequently, we would have a little hiccup every 15 minutes. So, that doesn't necessarily affect the throughput path, but it takes away back pressure on the latency path. And so, you can fine-tune things down below that millisecond, but you don't have to if it's not a critical path. And there's no more unexpected, weird, old-gen stop the worlds. They used to have intraday a couple of half-second pauses, unknown why, and it turned out that was back pressure. So they just happen, a couple times a week. They're gone, just gone. We done? Okay. So that's it. Summary. Java's wonderful for a lot of reasons. Java's both viable and profitable from a latency. I know that Zing is used here in New York. It's used in London. It's used other places. So it is the real deal. LMAX is a great reference for us. And you don't have to jump through hoops. You just write Java. And hopefully, you can, if you want, we can talk afterwards about if you have any use cases that are interesting. But it helps you be as effective doing low latency in Java as you could in another language. And then you get onto the interesting stuff, like making a better exchange. So that's it. Any questions? Sure.
I have two questions. Do you support Java 8?
Yes.
And what is physical deployment diagram for LMAX?
Physical deployment, Zing runs on bare operating systems. We usually specify 32 gigs of RAM, 6 to 8 cores minimum, so server grade. But we can also run on certain virtualizers, and we can also run in the cloud.
Like what amount of hosts is it spread about?
It depends. It depends on the size of your heap.
Yeah, like for LMAX, what's the working on configuration?
I think they are working in like the 12 to 20 gig heap range on a 64 gig Linux server.
It's one process.
Yeah, one JVM. It also depends on what you're trying to do. If you're trying to go low latency, you can get away with a small 2-socket, fast, but you're not going to load it up with lots of memory. But Zing works the other way too. If you want to have a 300, 400, 500 gigabyte heap for doing RISC or something like that, the same thing happens. You just don't get the sub-millisecond pauses. You just might have like 3 or 4 millisecond pauses. But to do that on a regular JVM, the rule of thumb is for every gig you add another second of GC time. So if you're in 100 gigs, you're waiting a minute and a half. And Zing, today, our GA version is 330, I think, gig heap maximum. But we have a version that's now rated for 1 terabyte, and that's going to go live to all audiences in April.
Just like because we have scaling algorithm.
Yes, yes. We had to change how many bits we use to track things. We didn't have enough. Any other questions?
I was just curious, what did LMAX use before? This system was the first one they built.
I don't really know. Sorry, I can find out, but I don't know off the top of my head.
I was just curious because generally trading systems, the first language that people even today they think is C++.
I think it was always Java. I think it was a different JVM, and they fought through the latency. People can use regular JVMs to do this, but they have to write different code to do it, and they can't use third party, and they have to build their own practice around low latency, no allocation free, lock free. It gets back to really difficult coding exercises at that point. And you lose all your productivity gains that you would have if you just were able to write regular Java. Or Scala, or the other JVM languages. I mean, we like those too.